Good. So sorry for the slight delay.
Can we have the same view?
No, it's over there. So now we have the second debate of this conference on machine learning for astronomy. And so we had like all these series of questions and more or less tough, we'll say. And the second one is, I would say, like a bit more wider, because it asks the question is, can machine learning models be considered on the same footing as physical models? So we'll see what our panelists will think of this question, and hopefully be enlightened or not at the end of it. So I think that, so we ordered, so first Hiranya Peiris here from UCL and Stockholm University also. Torsten Ensslin as second will be talking, and from MPA, LMU. Tom here, Charnock, who is is an independent consultant now, and Alan Evans remotely from Imperial College. So I will leave Hiranya starting on her viewpoint, and so this is here. You can change the slides, and I will put on the first one.
And is there a mic?
Yeah, your microphone is here.
Thank you so much. Can you hear me? Okay, so I think that a good way to start this debate is by saying what it's not about. And I personally don't plan to answer the question, are machine learning models useful in physics? So they clearly are. We have spent 2 days learning about many examples and use cases for machine learning in physics, including things like classification, exploring very large data sets, outlier detection, and also speeding up forward modeling and data emulation and so on. So they're clearly really very useful. I'm going to instead focus on comparing current, typical machine learning applications with physical models. And hopefully this will lead to some indications about how we can turn machine learning more towards physical models in order to even improve their utility in the exact sciences. So, so one way to start thinking about this is, what are characteristics of physical models? What do we actually mean by that? And I came up with this set of characteristics. So one is, a physical model actually follows from a defined finite set of principles and assumptions, and you can actually write them down. This would lead to a mathematical model that you can evaluate either analytically or numerically, and would yield predictions which are either deterministic or else probabilistic. The model is explainable in the sense that it's made up of ingredients which you can actually enumerate, and that are rooted in cause effect or other relationships that are grounded in domain knowledge of the field in which the model is being constructed. The model generalizes beyond the domain in which it was originally intended to be used, so then it can be used in other domains as well, so it has explainable power beyond its initial domain of construction. It also compresses information, and it provides explanations for a wide range of phenomena from a minimal set of ingredients. So it has, in some sense, captured some impact of Occam's razor. And its domain of validity can actually be defined and quantified in some way. So given this definition, there are two key concepts that arose there. So the ones that I've written down here is interpretability. So I've defined that as the ability to account for why a particular machine learning system reaches a decision or a prediction. And the second, which is different, is explainability, which is the ability to map that account onto existing knowledge in the relevant domain. So achieving these qualities is currently really challenging for machine learning because of the black box nature of many of the dominant algorithms that are being used in our field. So let's turn to the first one, which is interpretability. So this is the ability to produce outputs that help us understand why a machine has made a particular prediction and understand the computational working of the model itself. And this may be enabled by layering an additional system or calculation on top of the learning. For example, feature importances, symbolic regression, or by searching for an explorable internal representation of the actual learning of the machine, such as latent spaces in a VAE. This is also connected to generalizability. If the way that the machine tool actually comes up with a prediction can be understood, it can then be encapsulated in a smaller, more explainable model where you can use that model beyond the initial context of the machine learning tool itself. You can just take out the model and the machine learning will become irrelevant because you understand the model. So the trade-off between interpretability and predictivity can probably be understood because the accuracy of predictions probably diminishes as the size of the latent space is decreased, but constructing an explanation is easier if the latent space is small. Then explainability. This is the mapping from interpretation to domain knowledge. So explanations in science are usually based on relationships between states. An interpretation that can help capture or quantify that relationship or explain it to a domain expert, a scientist, then constructs the explanation after characterizing that mapping. That's what usually happens. There are also hierarchies of explanations. What satisfies one person as an explanation for why the model is making a certain prediction may not satisfy another. So our set of interpretability tools can't just stop at one level. It must help being able to query deeper and deeper into why a model is performing in the way that it does. And finally, the relationship between explanation and domain knowledge makes it immediately clear there's no such thing as explainable AI. There's only a set of interpretability tools that helps humans then understand and validate the explanations and construct a physical understanding of the model. Finally, there's this point about compressibility. Information doesn't exist devoid of context. So it actually always takes place in a particular domain. So the fundamental definition of information theory is the gain of the amount of information relative to an initial starting point. So once a domain and a model is specified, information theory allows the assessment of the degree to which the information can be compressed in terms of sufficient statistics. Again, this is clear that the level to which a machine learning model is parsimonious in the Occam-Racer sense has to be assessed with respect to a particular domain, and it doesn't exist in some kind of ether independent of that context. So informing human intuition to construct useful explanations then has to deal with the number of things a human brain can hold in its head at any given time. It's probably of order 10 independent degrees of freedom. We can't process information that is much higher dimensional than that. So that's the sort of compressibility that we are then aiming for in order to construct explanations. So in terms of going towards a common footing between machine learning as it exists today and this meaning of physical models that I've talked about, it's worth noting that many physical models that exist today do not satisfy my desiderata for explainability. For example, systems exhibiting emergent mesoscale phenomena, for example, structure formation and galaxy formation has come up in this workshop, where explainability is limited despite knowing all the microphysical ingredients that are going into the physical model. There are also chaotic systems where even though we write down the physical equations, the system is chaotic, so predictivity is limited. There are various interesting directions in the field towards interpretability, including things like saliency maps and sensitivity analyses, model compression, for example, using autoencoders, leading to disentangled latent spaces. That's something that I'm particularly really fond of in my own research. There's symbolic regression, there's effective field theory techniques that are being utilized towards trying to understand the principles of deep learning. Why does it work? And another productive approach, which has come up in this conference, is to use machine learning to accelerate forward modeling within large, complex, hierarchical Bayesian models, where there are data-driven components, machine learning parts, within the model, but the entire model is completely explainable. That is an approach that I think is very productive that I'm using in my own research. Finally, this is a dream. Okay, so far I discussed interpretability as relating to machine learning, where the machine's learning being interpreted by a human helps the human do physics better, okay? But can machines themselves do that final step? Clearly not right now, but I think there's nothing in principle forbidding that happening in the future. I don't think biological brains have anything special going on in them except having a huge head start. So on that optimistic note, I shall pass on to the next panelist.
Thank you. Thank you, Hiranya. So Torsten, please.
Thank you, Hiranya, for basically saying everything one can sensibly say about this topic. Torsten Ensslin. Can machine learning models be considered on the same footing as physical models? And my answer to
the mic is off.
My mic is off?
Yeah.
Okay, can machine learning models be considered on the same footing as physical models? My answer to that is not yet, but in the future, why not? Oh, it's not. That's terrible. It should come one by one. That's the problem. Okay. Huh? It's a PDF.
Yeah.
Oh, I have animations. Okay, let's go on. Okay, so what are the competitors to machine learning models? Well, that are the physical models we have. And here are three famous and very successful models. On the left, you see the standard model of particle physics, which is tested in zillions of experiments. Nevertheless, it is not a completely physical model in the sense that it describes the real world. There are things which are missing, right? It has neutrinos, but it does not have neutrino oscillations. And it has a number of free parameters which are just empirically fitted to data. But nevertheless, it's quite good. One thing which is missing is gravity, for which we have a beautiful theory. This theory allows us to do a cosmological standard model with a number of parameters. And most of them, like the lambda and the cold dark matter, are not part of the particle physics standard model. So also here we have a successful theory with free parameters that are fitted, which has some phenomenological elements. The third are galaxies, and there we are getting more and more phenomenologically, right? You can still do simulations of galaxies, but even there, ad hoc elements are there. And then we have also very phenomenological models of galaxy formation, which are close to what machines do with their many degrees of freedom of fitting. So yes, the machines are basically on the right of this diagram, but they might move to the left. Let's see where they are. So they start to discover physics. So what you see here is an architecture of a variational autoencoder. So on the left, you feed in data, then you have the encoder, which translates this data somehow in a low-dimensional latent space, which is designed in a way that the information of the data has to be compressed, and also some stochastic mechanisms ensure that some Bayesian elements are imprinted. And then you have the decoder, which tries to reproduce from this latent space representation the original data. So you have a high-dimensional manifold of things that can happen, which have to be compressed in a smaller space, and then reproduced. And the hope is that in the smaller space, you get a representation which is meaningful, even to us humans. And Sarah Milosevic in my group has done this experiment. On the left, you see a number of all-sky images, 37 is what she used. And you see this line where basically a brightness distribution data set was generated. So for each pixel on the sky, a data vector was created with the SED of that location. And then these SEDs were fed into a variation autoencoder in order to see if you can reproduce this and get an interesting internal representation. That machine had no idea about the spatial structure and no idea about physics. And on the right, you see some of the maps of the resulting latent space variables. On the bottom, you hardly can see that it reconstructs the dust map. Okay, Planck data was in. In the middle, you see that an X-ray map emerges. It's a map in behind. Okay, also the Rosat map was there. But on the top, you see something that looks like the CMB. And there was no clear CMB map inserted. So the machine realized, as a third most significant degree of freedom in the latent space, that something like the CMB is good in order to explain that all-scale data, without having any clue about spatial structures, physics, and so on. So it discovered something about nature. Then you can go on and look at other dimensions. The fourth map you see on top of everything, that's the fourth degree of freedom, and you see a lot of observational artifact being encoded there. So that is not human interpretable. However, the machine was not constructed to build something which we can understand. It should just do something it could understand by itself. And there it has already some success. Okay. We can help the machines to encode the physics by using architectures which already know about the physics. If you use a convolutional network, then you already encode something about translational invariance of physics. And my group is doing information field theory, and there we build networks that have physics or physics principles built into their architecture. Information field theory is about how to infer the structure of a field from data, so it's non-parametric Bayesian, and you can use things like Feynman diagrams to deduce properties. But in the latest time, we saw that methods for machine learning, in particular generative networks, are very powerful. And so that's how we do things. On the left-hand side, you see the Fermi satellite. And on the right-hand side, you see a map from the Fermi satellite all-sky image, which was constructed with a network, which you see in between. I'm sorry for that. Actually, this should have built up. Where you see the lower part of a hierarchical Bayesian inference network, which is written in a way that it is basically a generative model. So you feed in on the top white Gaussian noise, and you get out potential sky realization and potential data. Okay, that's the simulating part. And now you turn it around, you put in the bottom in the real data, and then you learn all parameters above in a Bayesian sense with backpropagation, very similar as is done in training a neural network. And the result is then this map and its decomposition in diffuse and point-like sources. So here, the network is built by a human and it knows about physics, and therefore it does not have to be trained. It auto-adapts on the data it gets in order to extrapolate where the data is not good enough. Okay. Yeah, this doesn't work at all, because this should have been a sequence. What you see here is a woman of age 33. She was generated by a neural network. But the point of that sequence of images I wanted to show you is that we ask the question, how can we start a dialogue with these networks, find out what they know, and ask them questions which are beyond the scope for which they were produced, right? If we want to trust the results of a neural network, we just have to make inquiries to it and ask it what it did understand and what it didn't. So in this particular case, the task was from a very noisy, low-resolution image of that woman to reconstruct her image, given the additional information that it's a woman and age 33. How did we do it? Here is the network we built. We didn't train this network. We built it out of pre-existing, pre-trained networks from the shelf. So the left network is a generative model for faces. It takes white noise and produces potential images. And then we have at the bottom a simulation of a camera, a low resolution camera, which produces an image which I couldn't show you. Then we had this age information, so we took an age detection network and fed the output of the first one in, and a gender detection network also from the shelf. And this gave us a data generating process which made this low resolution image, which you didn't see, the age and the gender. And then we used this structure as a, which is a generative probabilistic network, which has some prior component and some likelihood component, and did backwards Bayesian inference to the latent parameters in order to infer how that woman could have looked like. And unfortunately, I'm not able to show you that at this very moment. But if you go to this paper of Knollmüller and myself, then you find these images and the way we did it. And if you ask about the technical level, how we did this inversion, there's this MGVI, metric Gaussian variation inference method, with which one can do Bayesian inference backwards through differentiable probabilistic structures like neural networks or this information field theoretical systems I've shown you. And with this MGVI, we are able to not only go through networks backwards, we also are able to deduce Bayesian inference in 10 to the 8 dimensions. Okay, let me summarize. Can machine learning models be considered on the same footing as physical models? Not yet, but in the future, why not? They start to discover physics. Also, our physical models are not perfect. We can build in physics, and we can ask them, and hopefully also teach them to tell us what they've understood. So that were my statements.
Thank you very much, Torsten. So sorry for the He's here. So sorry for the hiccup, but you had to. You did a great job at interpolating the slides vocally. So the third element of the discussion is going to be brought by Tam Charnock. So if you can pass the Torsten, if you can give the the slides change.
Do we want to go straight to Alan next? Or
Okay, so maybe you can.
Either way.
Yes, and then we have to go back in slides in that case. Oh no, it's Alan first here. Okay, so fine. It's completely fine. Alan, so you want to step over?
Okay, can you hear me?
Yes.
Yes, I'm sorry not to be there in person. I came down with some bug, which means I don't have a lot of voice and I can't hear very well. So apart from that, everything's fine. I hope you can hear me all right. If my voice cuts out, it may not be the technology for once, it may be just my voice. So if we can have the first slide. Do you see it? I don't, so.
Okay.
I'm just seeing me at the moment.
Complaints on the Slack that they can't see the room or the slides, only they can see only Alan.
Yeah, well that's.
Okay, good, thanks. So after that beautiful overview from Hiranya and impressive examples from Torsten, I thought I would focus on a particular view and look at this from a Bayesian point of view. Can machine learning models be considered on the same footing as physical models? If we could have the next slide. Okay.
The answer is no.
So in my remaining time, let me look at this from a Bayesian perspective. Given that the subject of the meeting is astronomical surveys, I thought I would look at this from a focus point of view, looking particularly from a cosmological perspective, where obviously one of the many uses of surveys is to determine cosmological parameters. So we have an underlying physical model that we think is a good one, and we want to learn something about it. And the principal Bayesian way to do that is to construct the posterior on those parameters of the physical model. There's two very powerful ways for doing that, I would say. Bayesian hierarchical models, which Hiranya mentioned, and in the context of survey data looking for cosmological parameters, that's often field-based inference, where one is using the fields that one measures as the data, possibly in some somewhat compressed way, but not very, only lightly compressed in typical cases. And the other way I would say that you can really do this in a principled way, where you can really try to construct the posterior, is to use simulation-based inference, also known as likelihood-free inference or implicit likelihood. And these methods, I mean, in a sense, they are both machine learning methods, but I think that's not really what we're talking about here. Usually these are based on underlying physical models. What they do is to avoid the usual compressed summary statistics, which may have incomplete information and poorly known sampling distributions. And they should do better because of their use of essentially all of the data that's been collected. If I can have the next slide. Previous one, this one, yeah. So I think one of the uses that we think of machine learning as being particularly powerful is if the model is very complex, or if the data model is very complex, and the physics may be extremely difficult to model. What I would say is that I think physical models can deal with very complex data sets and tease out all sorts of information in a very powerful way. And I think the best example of this is Borg, which we've heard about before, where by constructing a detailed data model that is built in layers with a hierarchy, starting with the initial state where you know the probability distributions, using a physics model, a gravity model to generate final state. And then you have in this case, a bias model that gives you the galaxy distribution, which is then compared with the data. So here in this slide, which I've shamelessly stolen from Jens, you see Borg in action. And of course, one's going backwards from the data to the initial state. So we do have tools for dealing with highly complex data sets and really complicated models that don't involve the machine learning techniques that I think we're really talking about here. And you can see the power of this in many examples. One very recent one on the next slide is from my colleague Natalia Porquerez, showing what it can do for weak lensing, where the matter clustering and the matter density parameter from 2-point statistics is it always recovers a banana. But if you use this field-based likelihood, then it lifts that degeneracy extremely nicely. And the marginal error on the matter density parameter is reduced by a factor of 5 in this example, this simulated example, just by using all of the field-based data rather than using summary statistics. If we can have the next slide. So why not just do it this way? I mean, why not just do the big Bayesian hierarchical models for this sort of study? And I think if it's possible, then there's no reason not to. But it's challenging. It's challenging because it's expensive. The sizes of the data sets are large if you're using all of the field values. You have high dimensional parameter spaces, which can be up to 10 to the 7 or even larger. And physics model is relatively expensive to include, and one's doing a large number of forward simulations in this process. In general, you know, you may have complex physical processes that go beyond n-body, and that can lead to model misspecification, where the physics model that you put in is not the correct one. And as Ben stressed at the beginning of the meeting, that model misspecification can be very serious for this sort of approach. And the examples for galaxy clustering and indeed for weak lensing are galaxy bias and baryon physics, for example. And these are things which I think are difficult to model from fundamental principles. And I think this is where machine learning models can certainly help. Machine learning can play a very significant role, I think, in these Bayesian approaches. As we've heard on and off today and yesterday, acceleration via emulators can speed up the forward modeling approach. And there's some examples there. I just want to draw attention to one, and that is EMU-PK, which was developed by Harry Mutuvalu. I highlight it simply because he's completed his PhD yesterday, and so congratulations to Harry. And the other place I think where machine learning can really be used is to approximate submodels within the Bayesian hierarchical model with machine learning models where we have a poor physics understanding. I think where we have good physics understanding, it makes sense to build that into the model, but in the bits where the physical model is difficult to work out from first principles, then machine learning could be a very useful way, I think, to deal with uncertain parts of the model, which could otherwise cause severe difficulties in the inference problem. So I think we see that the machine learning can play a very significant role within Bayesian inference, but it's not really, I think, here a full machine learning model that we're describing. If I can have the next slide. So the other way to do this rather than with BHMs is to use simulation-based inference. And here one is essentially learning a probability distribution. Ultimately, the thing one is looking for is the posterior by simulating. It's a very Bayesian approach, really. It's essentially sampling, well, there are various ways to do it, but sampling the joint distribution of parameters and data. So within the context of a physical data model, we have here some powerful machine learning techniques which are being used to support a physical model being used in a Bayesian way. What it requires is extreme data compression. This joint distribution of parameters and data would be clearly impossible if the data set was 10 to the 7 dimensions. So you need to compress the data massively down to the sort of number that Hiranya tells us that we can hold in our heads, and I think she's probably about right. So, you know, of the order of 10, which requires massive data compression using something like moped score compression, or indeed here, I think this is where machine learning techniques such as neural networks can play a role in finding the optimal compression statistics that can be used in simulation-based inference. And here I think one's on a very good footing, because it really doesn't matter how the black box got the answer. If it gives you some statistics which have optimal information content, then, you know, sort of who cares how it worked them out? You can still use them. And if they're not quite right, then they'll still be extremely useful and still get you almost all of the information out of the data. The other role that machine learning plays in this sense is in the density estimation of the PDFs. These can be quite high dimensional, so using some sort of neural density estimation is an attractive way. And all of this, I think, is very effective in its uncontroversial use of machine learning. And it's really facilitating this principled Bayesian inference, both in the case of simulation-based inference and in the Bayesian hierarchical model. If we go to the next slide, which I think is the last. So just to generalize beyond what I've said, so what I've said so far really, as I say, doesn't address the question of whether one can build an entire, or whether it's sensible to build an entire model, data model, which is based on machine learning. Focusing on near-term goals, I think the answer is that it's difficult. In the long term, I think, you know, maybe, but it's I think quite speculative to see what would happen in the long term. But I think the key point is that what we want out of this process are probability densities. We don't want numbers. If you give me a number, I'm not sure I know what to do with it unless I know its distribution, if you see what I mean. So the uncertainty quantification is key to this. And there are some inroads into this, but with, for example, Bayesian neural networks. But to be honest, I think Tom's going to talk a lot about these in future, so I'm not going to say very much. But I think here, yes, they are strictly Bayesian models, but I think what's happened is that one has a sort of empirical predictor from the neural network, which gets promoted to a data model, but it's a pretty weird data model to pretend that the data is created in this way. Of course, the neural networks can approximate all sorts of things. So as a process, it can represent all sorts of different underlying physical models. But I think the difficulty perhaps comes in trying to interpret the errors that you get from this, from, let's say, prior distributions of weights, which is, I think, a very sort of technical definition of a Bayesian process. Don't get me wrong, I like these things, but I think the interpretation of the errors and the validation of the uncertainties that you get from this, I think, is probably something which still needs further work, shall we say. And finally, just to finish, looking into the future, then clearly everything that I've said so far has been model-based. So if one is looking beyond the models that we're considering at the moment and looking to see if new models are required, then with the flexibility of machine learning models, then there's clearly some value in being able to explore a wider range of models. And the flexible modeling can be an advantage. It can also be a bit of a curse, I think. How much more flexible do we want it to be? I think Tom is going to look at these questions in more detail, so I'll stop there and pass over to him.
Okay, thank you very much, Alan. So now we are our last speaker, our panelist, to expose this viewpoint, so Tam Charnock. So we got the, well, here's the requirements. Yeah, it will be great. No, and?
So I've taken a slightly different tack on how to answer this question. So the other panelists have really looked at, can we use machine learning to do physics and make physical models? Or I'm kind of interpreting the question quite differently as, what's the difference between a machine learning model or a neural model and a physical model? And I can't say that I necessarily, I'm hoping to provoke some debate. I'm not sure I can actually definitely defend that point of view, but I'm going to try and present it anyway to open up some discussion. So my answer is also no, they can't be considered on the same footing, but also a little bit yes, because there's a lot of similarities between the two ways that the two different ways you can look at these as different models. Now, one of the ways that I like to think about neural networks, I'm going to talk mostly about deep learning and neural networks here, because I think that's kind of what people are interested in. And I've been told by many people that this is my viewpoint is not a particularly useful way to think about neural networks, but I like to think of them in this way anyway. So I want to say that the way that I always think of neural networks are as a probabilistic model. So that is, the neural network is just some way of some kind of probabilistic model where you want to fit a particular set of data or a certain relation based on the parameters of that model. So that sounds like a physical model to me. That sounds like something where you want to be able to infer some data given some parameters. And here it's just a bit strange, because when you're talking about a physical model, you're talking about, I'm going to think about the properties of that data, which I want to infer the parameters which describe that data. Whereas here you make an architecture, or probably you grab one from the internet and you don't care. But the fact that you've grabbed that particular model and you've defined a certain loss function and you've got some certain distribution of data that you're going to train it with, that defines a metric over which which we can think of as a likelihood function. So that is that there is some distribution of weights, and we can get a value out of the neural network, and every time we change the value of that weight, we can get a different value, and some values will be closer to the answer that you want or not, and that's very much like what the description of a likelihood is. Let's say you want some result, and that result is more likely, then it would have a higher likelihood. For me, I find that quite an intuitive way of thinking of things. This doesn't need to be what everyone else thinks. I'm just saying this can be opened up to the debate. But if you think of them as that way, where you've got some likelihood, which is described by the value of your loss function, and you want to say how likely is your data given that you've got some values of the parameters, and you've got some distribution, that possible values that those parameters of the network can take, then you can also do posterior inference. And in fact, that's really how we're fitting neural networks anyway. We're not doing it very well, because we're just going to do a maximum likelihood estimate on that, on the values of the weights, and then we're going to stick to that one single value of weights and say that's the answer. But the actual framework in which that works is a very Bayesian one, like Francois said yesterday, but we just never use them in that way. So the fact that they're not understood in this way, why can we actually, this implies that we can't consider them on the same footing as physical models. So the main reason that there's lots of downsides to using neural networks as instead of a physical model, and that's generally down to how flexible a neural network is. So if you could fit any function, then with a certain subset of the distribution of data that you could have and some certain initialization of your network in any possible network, then you've got no meaning to any of the parameters in that model. So this is, in a way, it's not comparable to a physical model, because in your physical model, then you have lots of parameters which have some physical meaning, which have some impact on the way that data is generated. But with these neural models, if you've just got weights which are fully connected weights, then that's really abstract. You can't really interpret what those individual parameters are saying. And the reason is that with a physical model, then you're building in physical symmetries. You'll find out some way that one believes that the data could be generated based on our opinion of what is a way to generate that data. So that's a physical model. And that means that if you want to predict some other data in the future, then you can maybe say, well, it has to follow these certain symmetries, so I can probably, extrapolate some distance. Whereas when you don't have the symmetries in there, then how can you say what those weights the values of those weights should be, to be able to say that they've got some physical meaning, and I know that it's not going to predict something which is completely out of distribution to what you expect. So in this way, the neural models don't have that safety due to the symmetries unless you start to build them in. So we also mentioned yesterday a bit about deep priors, where the type of architecture that you use, or the way that you're training, or your loss function that you choose, defines a particular, well, I would say a likelihood, but there's a particular set of functions which are available when you choose a certain set of architectures, or you limit them, so you can get some way of extrapolating further, maybe by being slightly protected. But the problem is that when you're really, really flexible, then, and you've only got a subset of all the possible data that could exist, then you're going to fit, if there's anything spurious because you've only got a subset, then that will be fitted, and then the extrapolation will also not be very good because you can fit a very, very flexible function which doesn't have an interpretable meaning to it. But having said that, I don't necessarily see that there's a difference between the two in a Bayesian sense, but they're just coming from different directions. So if a model is overly flexible, I'm not going to believe it because I wouldn't believe necessarily a prediction from that model because I don't understand what it's doing. But that's true for a physical model as well as a neural model. If I don't understand what the physical model is doing, then why should I believe that? And that's part of this Bayesian thing where we have a prior for what parameters we believe on what models we believe even. But obviously we prefer things like Hiranya said, where we want to specify a model based on physical principles, and we can use Occam's razor to try and reduce the complexity to make the most general model which describes our data well. And so when you're following those principles to build a physical model, that isn't necessarily what you would tend to do with a neural model. And so that way you separate them again. But if you just keep reducing the types of functions that you use to make a neural network, so you reduce your network down from a 17 million parameter model down to one which has got two models, which is two parameters, and it's just a linear fit, then what's the difference between those two things apart from how many layers there are, how much complexity there is. So reducing that complexity in the network and making the transformations that the network is doing to generate the data, it just starts to become something which looks more and more like a physical model. And so the question is, when do we say, well, this is a physical model because it's influenced by physics, or this is a deep learning model because it uses a convolution? But that convolution could be very well physically motivated, but you might not know the parameters of that convolutional kernel, for example. But if you use that in your physical model as part of it, then maybe that's still got physical meaning to it. So there is an interchange between these two different things. So I just want to say that if we don't understand the neural model, then if we don't understand how we get particular results from the network, if it's not interpretable, then how can we extract any physics from that and any meaning from that? That is a question, but I've written it not as a question there, just to be provocative. The problem is then if you want to use a physical model and then wrap up some really large, uninterpretable neural model within that, so doing acceleration within a physical model, but you don't know if your neural model is doing something which is physically relevant because you don't know about how it will extrapolate and predict, then that biases the entire physical model when you want to do any inference. So why is that a good time to try and build it into there? And what's really interesting is that believing the result of a neural model, I feel like has a very close link with how you choose your priors in a physical model, in terms of if you choose, I might not believe some set of prior results. The priors of some parameters in a physical model might be affecting the results in a very drastic way, and that could really mean that prior isn't believable, and I don't believe it, in the same way that someone could give me a result from a neural model and say, well, just believe it, but why should I believe it without having some evidence that that's not affecting the results? But I just want to end on saying that I think the real benefit of these techniques is that we've got a lot of money from the industry, which means that we can develop super effective frameworks which allow us to accelerate computations massively on GPUs, and so building like Bayesian hierarchical models becomes easier and faster because we can accelerate these using the exact technologies which are being used to make neural networks. But if we've got that same kind of acceleration, then maybe we should be focusing the effort on there rather than choosing the thing which we're not sure of. Which doesn't answer that question at all, but it's a point I wanted to make. But I'm going to finish there.
Okay, thank you very much. So for the 4 viewpoints first. So maybe before I maybe chat about something, so is there any questions from the audience for the 4 panelists? Don't hesitate. Who has a microphone? Who stole the microphone?
Hello, thank you very much. Listening to all the different points, it looks to me that, in fact, the main thing that is missing at the end is interpretability. You need to understand what are the parameters and uncertainty quantification, okay? So if there's, where's the limit according to you, where there's improvement, for sure there will be, because there's lots of people thinking about that. So there's no reason to think that the interpretability methods will stop at the level we have now, and there's no reason to think that uncertainty quantification in neural networks will stay as it is now, which I agree it's quite limited. But where, or is you think there's an avenue for, where do we say, okay, now we got a good method, or how do we look at that? In saying, okay, I have a reliable interpretability method that I can think, and then, okay, I can understand my model even if it has millions of parameters, but I can understand it properly, and so then it becomes a physical model in some sense. Or do you think there's a bar or threshold we should reach?
Well, at the moment we are using the universal function approximation ability of the networks to have things which behave than other things. And I think that is largely, so we have very good emulators. There might be, hidden in these emulators of input-output relations, there might be already the core of abstractations or concepts which it is discovered over
closer.
Which is discovered, the network discovered about the phenomenon. But how to dig them out, I think that is a challenge at the moment. So I believe that some of the networks have interesting insights, but we haven't found out how they can tell us about that. And some of them are just phenomenological fits to something. So at the moment, we are in a very noisy regime of understanding what is encoded in weights and these functions. But it doesn't have to stay that way, right? And probably we will have other networks which at some point translate what they see in a network in human understandable language. Because the connections might be very complicated.
Just asking you a question on that, how would you trust the output of the network which is explaining what the first network was doing?
I would ask a question. So it has to be, it cannot be that it just gives me an explanation, that's it. I must be able to question its reasoning and say, okay, what would you think happens when that? So that was what I was trying to say with this conditional network which we built out of existing networks. That was a machine which answered a question which it was not built for. It was in the scope of its world, but it was not particularly trained to answer, so the components were not particularly trained to answer the specific combination of question. So that was one attempt to get closer to that. But in the end, it must be a dialogue. So the machine should not expect the question I will ask it. And then if it is able to answer them, it makes sense, then I'm starting to build trust.
If I may add to that, so I think that the main problem is that even though the neural network has dimensionally reduced a very complicated data set to a flexible model, that remains really high dimensional. And I agree that the key is to understand what the machine has learned that actually allows it to generalizable predictions, and that's very hard to extract out. So currently, I think the available dimensionality reduction methods that allow us to interrogate what the machine has learned are quite limited. Approaches like variation autoencoders, for example, even though they allow you to compress the machine learning model down, that probably comes at the expense of predictivity. There's a trade-off between the size of that dimensionality and the predictivity. And so I would assume that we would need to develop further such ways of taking very accurate machine learning models, which are very high dimensional, and compressing them even further. Regarding your question about uncertainty quantification, what I see in the machine learning literature about this doesn't really seem to me to be very, so the Bayesian interpretation of uncertainties is very ad hoc. I don't find it at all satisfying. And I see much more work towards this model compression aspect that seems promising compared to the uncertainty quantification aspect.
If I could add something on the uncertainty quantification, I think I'd like to see more work done on the validation, say, training the networks on known physical models and seeing what the posteriors look like. Now, clearly, you can't compare the parameter sets because they're completely different in the physical model and the neural network. So I guess that would have to be in the data space, looking at posterior predictive distributions and so on, just to see if can they learn a physical model and provide uncertainties for that. And then the question will be, well, okay, if it can do it for that particular physical model, does that generalize to other ones that one might want to explore?
Yeah, actually, I think that's exactly on the point on one of the Slack questions by Paco Villascueza, who was asked you, actually, Alan, I wonder if we are okay with neural networks giving us posteriors and parameters in a way we don't understand, and are we also okay trusting these posteriors if they lead to big discoveries, such that ruling out lambda CDM or measuring nutri mass below 0.06 EV? So that's his question. Okay.
As they say in the British Parliament, I refer the honourable gentleman to my previous answer. I think, yes, it's the validation, I think, that would give us at least a little bit more faith in the results.
Xiao?
Hi, thank you. Is it working?
Your name? And
I'm Xihao Cheng. I have two general questions. So to me, the difference between a physical model and machine learning might be that one is we now can communicate with other people using the physical language, and the other is it seems for physical models you have some mathematical background behind it to help us to transfer the validity from like one statement to the other one. Right. So, so concerning these, I wonder how would you comment on when we will have the ability to communicate with neural networks, and also for the validity problem, I remember some holes in the neural networks. Right. There are some adversarial examples. So. Yeah, so about the adversarial examples, how would you comment on that? What's the state of that now? How well do we understand the properties of the trained machine neural networks? Thanks. For all of you.
Maybe Tom, you want to start?
Yeah, so I maybe I'm a bit skeptical, a bit more skeptical, or I'm not sure that there's going to be a point where we can interrogate a neural network in its current form to be able to tell us what we want. I think we can probably already do, as scientists, we might be able to do things already where we take existing networks and do sort of, almost relatively classical correlation between latent spaces and things that we want to understand, or we've seen this a lot being talked about already with sort of where people are using sums, and you can, if you map colors onto those, then you can have a look at a person can have a look at that and then try and work out what that means in some sense. I'm not sure that's what I really necessarily think is the way forward for doing science with neural networks, but that's a way where you can, use a human to understand to do some science with the output. But I'm not sure that I'm not sure that the current form of machine learning would allow us to actually interrogate it in this way. Maybe other people might have other opinions.
I think my answer is very similar to Tom's. I think currently the way that we can best use them in the sense that you mean, which I agree with, is actually to use them and trying to study their learning process to inform human intuition. And then the human then goes away and builds the physical model and expands human understanding. So that's the way I think about it as well. I think the fact that the development of machine learning is primarily driven by industry and their goals may not be the same as physical scientists trying to do better physics might lead to the tools we need not being developed, right? So I do agree with Tom that the main thing that we've got out of this is this incredible capability to accelerate our forward modeling calculations. Machine learning is just a tool. I mean, I don't particularly see any utility in saying, I want to use machine learning to do physics. I want to do physics, so then I'll take whatever tool that comes and only use it if it's actually useful for the question I'm trying to answer. So I don't know whether that addresses your question, but it's just a tool.
Yeah, I agree, we are not there, but I think we should aim for that direction. Right? We should try to build our architectures in a way that as much physics is built in, that we can read out as much physics as possible, and think about ways how to extract these things. While just saying, oh, there's a black box and we can't do much about that, I don't think that this should be the direction of our own academic research. So that's why I'm trying to push in this direction. Thanks.
Maybe Nyal?
I don't have anything further to add.
Alan, you want to make a razor point?
No, it's all been said. So.
Okay.
Can you hear me? Yeah. Hello, it's Niall Jeffrey. Putting aside the using machine learning to, as Alan said, to basically calculate densities from a forward model that you already described. Going on to Tom's idea that you can somehow treat the neural network on the same footing as a physical model seems quite worrying to me, and I assume that he said that on purpose, is trying to make us seem worried by this. But as Hiranya said at the start, it's really important when you're understanding, or you're understanding what you're understanding, it's important to know what you're coming from, the prior things that you already knew and what you have learned from something. And given the possible outputs of an untrained network just cover every possible output, basically, it then seems very unhelpful to start trying to turn the loss somehow into a likelihood in that model space. You can do it mathematically, but it doesn't seem like a useful thing for physicists as a framework or a way of looking at these networks. Sorry if I covered too many things in one ramble.
Did you have a question? Or?
Did you have a question or rambling?
You can infer the question from all that data that I just gave to you. Okay, I disagree with you, Tom.
That's still not really a question. I mean, I was saying that to try and spark a bit of debate. For me, it's a case of how do you look at the uncertainties of what neural networks give you, and in a space of near infinite different outputs, you can find, you know, a particular value with a particular set of weights, which you might be happy with when you've done some training, but you don't know the uncertainty on that. Now, if you then go back into that there is a landscape of weights where there's lots of possible functions which would describe how, you know, okay, maybe how close you are to the target which you want to achieve. That metric there is to me is the same thing as what a likelihood is in some sense. And so that's what I'm saying. It's just a way of interpreting it. But I agree that there's the meaning behind those weights is really hard to capture. So I'm not saying go out and then sample all 20 million weights in your network and find out and then marginalize those out to get the uncertainty on the thing that you want to predict. But if you wanted to know what the uncertainty on that thing is that you wanted to predict, that's what you should do. Which then goes to why don't you just reduce the size, the network down to something which is actually physically relevant, or just a physical model, and then those uncertainties mean something, and so there's just, you know, reduce the size of that network down and down and down and down until you reach a physical model, essentially, and then that might be useful. No questions.
What did the other panelists think, I suppose, is what I want to know as well.
So there was a question on the right here.
Here we go. Hi, Florent Leclerc from Imperial College London. My question is, actually, I guess, for all the panelists, maybe particularly for Hiranya, since you mentioned Occam's razors as part of the desiderata. So assuming we get to a stage where machine learning models and physical models are on the same footing, or where we have perfectly valid hybrid models, would you say that traditional Occam's razors and evidence calculation is still the right thing to do? Or should we actually rethink Bayesian model comparison? Or in other words, maybe should a model be penalized just because it's machine-based and not human-based or physics-based?
Thanks for that question. I'm not one of those people that thinks machine learning encompasses Bayesian reasoning. I think Bayesian reasoning came first, and which will continue to provide a probabilistic framework for scientific reasoning. And I don't think it really matters where, I mean, we're talking very futuristic, but I don't think it matters where a physical model came from a human or meat brain or a machine brain. They should all be you know, evaluated following the principles of probabilistic reasoning. Sorry for the slightly facetious answer.
Torsten, you want to say something?
I agree fully. Occam's razor prefers models with a low number of parameters. That's not always the thing to go for. Sometimes we know things are complex, and then you need a complex model for something complex. But if you take this into account, I would completely agree, calculating Bayesian ratios and odds ratios in the Bayesian way is a way to go forward. One thing one should look at is how is the model built? What is there? Are there abstract concepts involved? Are there symmetries? Well, basically all physics can be derived from symmetries, and there is no reason why not networks can discover symmetries and represent them somehow, or we build them in. So they might get as aesthetical as equations, and probably are just a different way to express an equation. And if we find the language to basically implement our aesthetic principles, which are guiding us through theoretical physics on networks, then why not having something which has 1 million parameters? As long as these parameters are guided by principles we think are the foundation of physics or the science we are looking at. I'm not saying we are there, by no means, but I don't think there's a conceptual problem because, well, otherwise we couldn't trust what our brains are doing, right?
Sorry, may I quickly come back on that? I think Bayes' theorem tells you that two models which are equally predictive are on an equal footing. It doesn't necessarily penalize a small number of parameters. So I think we agree, but yeah.
I maybe just want to carry on from what you were saying, and that the neural networks we're using at the moment, we're considering as a universal approximators. So we're trying to work out, we have many parameters in there so that we can find a relatively simple function within that space of possible functions. So if you could, like, this is the bit which I don't know how to do, and I don't know if anyone knows how to do particularly, is if you could extract that function out of there, there is a certain number of degrees of freedom which isn't as many parameters as there are in the network, which represents the function. There's a function which has fewer degrees of freedom in there. And so it's that function that you need to be evaluating the number of parameters of, not the number of parameters in the entire network. So it's not like you have to, divide by log of 20 million. It's when you're doing the evidence calculation, it's something else.
May I add something to that? So in the application of information field theory, we do non-parametric reconstruction of density fields, magnetic fields, and things like that from data, and usually the data is much more sparse than we have. So what we use is the existence of correlations. So here we say there are spatial coordinates, and if I know a quantity at one location, for many physical quantities, its value at a nearby location is similar, and these correlations can be exploited. So they are a consequence of many physical laws. And so and you can increase the number of degrees of freedoms in this reconstruction by a factor of 10, and you get basically the same answer. And you actually also can calculate evidences, and they stay a finite number. So the total number of degrees of freedom you use to represent something does not need to be a limiting concept. If you can put reasonable symmetries and correlations and principles on top of that, the number can virtually go infinity without evidences exploding.
Maybe before going to the questions there, so Alan, do you want to finish on that topic?
Yes, it's an interesting question. I wouldn't treat them differently. I think if you have a machine learning part of a Bayesian hierarchical model, or indeed a machine learning model overall, then you've constructed a data model with some parameters in it. And I think one would really treat it in the same way. I think the example that Ben gave yesterday of a neural network-based bias model, some submodel of a Bayesian hierarchical model. I forget exactly how many parameters it was, 11, I think. If that's what's
17.
Needed, 17, okay, all right. Of the order of the Hiranya number, order 10. It's if a simple model with bias model that has only a few parameters and gives you likelihoods which are low, then it's not going to be favored by the evidence. So I would treat them in the same way.
Just for that problem, then every single one of those weights in that 17 parameter model was meaningful. So they had meaningful priors. They were essentially physical parameters. So that it is different in some way to something which is much more flexible. This was just absorbing what we didn't know, but we knew a physical symmetry for, I guess.
Maybe Emma?
Yeah, so there is some question on the Slack. So firstly, there is one from Nguyen Guo, which is asking, regarding building physics into models, can you share insights on how we can go about drawing a line between incorporating prior physics knowledge and biasing the model towards only known knowledge, and hence prevent the possibility of discovering new insight on a problem using the network?
So Yeah.
Alan?
So, I mean, we do have tools for determining or giving some insight as to whether the data models that we're using are good predictors of the data. I guess the posterior predictive distributions can be useful in indicating whether we need to go beyond what's in the model. So in terms of sort of diagnosing the problem, I think we do have tools. Then I think the question is, what direction do you go in making the model more flexible? And I think that's sort of opens a Pandora's box, really. You could go in any direction you like, in a sense, and maybe neural networks or other machine learning techniques would be a way to explore which directions you need to generalize.
Shall I answer? I think my answer to this question is more philosophical. Humans are capable of discovering new physics. We've been doing it for quite some time. And I think this is just a new tool in which we can utilize it to discover new physics. A machine learning model is entirely based on its training data, right? So that defines the problem it's trying to solve. And if the training data is representative of a particular type of mapping, you can imagine we can discover new relations that were previously unknown by studying its learning process. I'm not so concerned about biases. I think humans have biases. Machine learning also has biases. And we also have the scientific method, which is our way of our species to de-bias ourselves. And I'm confident that will continue to work in the era of machine learning.
I would maybe just add that this isn't a problem which is necessarily just related to machine learning. This is just when you do science, you only get some amount of the data, and then you want to know, is that data representative? And so it's not really a machine learning problem. It's just how do we collect data?
And there was a second question, and then.
Okay. So the second question is from Jenny Wagner, and the question is, do you think the approach from mathematics to relate neural network to kernel method is promising? Proceeding on this direction, we may get mathematical robust statements about the convergence, the optimality, etc. All that helps physics.
Sorry, I didn't get the question.
Yeah, so do you think the approach from mathematics to relate neural networks to kernel methods is promising? And pursuing in this direction, we may get mathematical robust statements about the convergence, the optimality, etc. Would that help physics?
Oh, so my point of view on that is that all of these things are really, really based on going to the very limits of like infinite amounts of data and infinite amounts of weights and all sorts of really statements that we don't get close to, and they don't even seem to follow exactly the same kind of trends as they approach in large numbers. So I'm not sure about that. Mm-hmm. But that maybe I'm just, again, overly skeptical.
Yeah. Hiranya, if you want to...
I'm not fully sure I understood the question, but I've recently found some interesting work on using effective field theory to study various limits of the sort that Tom just talked about, but without needing to go to extreme limits like that. And I think that could be a promising approach. Maybe this is a way that physicists can actually progress the machine learning field. But I've only just started to read about it, so can't comment in detail.
Yeah, I'm also not an expert in this area. So what I've seen is that people do simplistic model of machines that learn, and then study those in order to get an insight on how the more complex models learn. And then, of course, it's a big challenge to mathematicians, and we hope that they tell us something about what are the functions we are using when we use one of these universal function approximators. It turns out that they are very good in folding manifolds in a complicated way into other spaces. They have to do it in a certain way. And that's clearly something where mathematicians might help us to understand what's going on. What are the pitfalls in doing that in machines or in human brains? But I can't answer where the status of that research is right now. Sorry.
Yeah. I think it's a really interesting question.
Yeah, Alan, if you want to conclude, yeah.
Yeah, it's a really interesting question. I don't know enough about this to be able to say anything more on it, but interesting question. Thank you.
Yeah, so I was sitting over there, but pressing my hand, but I think you just at a dead angle with that black thing. In fact, there's another question in the air. Yeah, so this is a bit of a thought experiment, but as you all have different opinions on machine learning, but also in different ways, cosmologists, imagine that tomorrow someone took all data from galaxy surveys, the CMB, put it through the CNN somehow, miraculously, and came up with a model that is kind of like Lambda CDM, but with a couple more parameters that do something. Would you believe that, considering Lambda CDM is already a phenomenological model in a lot of senses? Or what would it take you for you to believe that?
So you're talking about the CMB data. I know a little bit about the CMB data was processed and about the pipelines, and some of the people who worked on that are also in this room. So there would be a number of questions I would have to that machine. Show me which point spread functions you used. Show me what you did with the noise. What was the instrument response function? All these tons of questions about concepts we used in our analysis. I would like to see them that they are in some way represented there. But then if that machine shows all this, then why not?
Yeah, please, Alan, we were just discussing that actually that's the last question of the week, but please give your viewpoint in advance and we'll see at the end of the week if we still agree.
Yes, so I think I would apply the same rules that I would apply to any other model. As I say, the machine has constructed a data model, so you can, I think, test that data model with standard Bayesian techniques, Bayesian evidence, and so on. But I think for something like that, I would probably want to see more. I think you said that you would put all of the data in and learn something from it, and that's maybe not the best thing to do. I think it would be probably better to train it with some of the data and then to look for predictions for what the other half of the data would be, and do some sort of validation to see whether, using large-scale structured data, for example, it can then account for strange things in other data sets. So I think with something like that, then the standard techniques, yes, but I would also perhaps look to see whether it could be predictive in the sense of training it only on some of the cosmological data and see what it did with the rest.
I completely agree with the previous speakers, and I would add to that Lambda CDM, sure, is a phenomenological model, but it fits within a framework which is based on physical principles that we understand, and we actually understand what we don't understand about the phenomenological components. So the machine better tell us a characterization of its extra parameters that allows us to put it into the framework of physics that we already have, and to be able to interrogate those components further with the data that it didn't use.
I would maybe just add that it might be interesting if you'd set up that magical, very fast-running CNN to get it to project out like orthogonal bases. And so if there is information like non-zero variance information in there, in some of the extra parameters, then maybe that's interesting. But then maybe you would just do the same thing with like a giant PCA or something.
Question here? Yeah.
Karen Henniker, hi. So usually we say that the networks to learn what's on the training set, kind of intuitively. So there's been some kind of really toy studies where people try to show that you can use generative models to get some extra statistical precision beyond what was in the training sample. But just using really like a camelback function, really simple toy models. And I was curious if what you think about that.
Are you talking about denoising a machine learning model?
So basically, I think they've shown it for generative models, where in the end, statistically, your generated sample has more information that fits better, like the true underlying distribution, than what your training sample had. So but it's beyond just simple interpolation. So it looks like it learns shapes or something that's beyond interpolation.
I think if I've interpreted your question correctly, I think that you're saying that even though there was a noisy training set, there was some universal relations hidden in, like a lower dimensional set of universal relations hidden in that training set that allowed the model to make sharper predictions than was warranted. Have I captured your question?
You may, so actually it was not noisy data. So that's kind of, I think it's really debated in computer vision right now, if it can learn something that's not in the training, basically true. Yeah.
Maybe someone else can pick.
Well, so I think there's a chance that a neural model could learn some representation of a physical model, and you may be able to generate something according to that physical model that you've learned, which, that might give you more small-scale statistics, say, than you would have if you just had the very few simulations that you had. But I don't think there's any way of validating that without it being just as expensive as running all the n-bodies you would need to do it anyway, to actually know that you've not biased your result. Or for me, that would be my I wouldn't necessarily trust that I'd got more information out of the generative network without testing that so much that I might as well have just done the physical model in the first place.
Yeah, maybe Torsten can finish. We are going through the last round.
well, these models can be very creative. So if you play with these, for example, face-generating networks, they can produce very artistic images of humans or pseudo-humans which have patterns which real humans don't have. So they do things which are not, they leave the realms of what is real in creative ways, and you have to be aware of that. And so testing, as you said, is a protection against that.
Alan, you want to say something to conclude?
Nothing further to add to what's been said.
Okay, so maybe we can call it a day. It's 7:40 p.m., at least in Paris. So thank you everyone for staying that long, and we had a few hiccups this afternoon. So maybe a round of applause for them. And one for the regie also, because so tomorrow we start again at 3 p.m. Paris time, so we have a morning free. You can sleep over if you want. And see you tomorrow for the continuation of the conference.